quiet, I'll go ahead and introduce today's speaker. Dave Scott is currently the Director of Imaging Systems at Intuitive Surgical. He holds a BS in Aerospace Engineering from the University of Kansas and an MS in Aerospace and Biomedical Engineering from here, University of Colorado. He spent the last 17 years in research and development related to medical imaging and diagnostics. He's also a co-founder of Varioscale, a startup venture dedicated to bringing ultra-high resolution laser etching technology to the semiconductor and life sciences communities for lab-on-a-chip applications. Dave has been awarded several patents in X-ray and medical endoscopy applications, and he regularly works with startup companies developing strategies for technology development and product positioning for acquisitioning or licensing. Go ahead.
All right, thanks very much. Yeah, so I graduated from CU, that was a long time ago now, so it's changed drastically. I didn't recognize even the buildings. I think they've added a bunch of new buildings around here compared to when I was here a long time ago. So I was in the aerospace. Anybody in the aerospace department? No? Okay, I'll have to stop by over there and say hi to some folks. I'm also a big Buffs fan, but now I'm a Giants fan by watching the game. Yeah. Okay. I live in the Bay Area. That's where Intuitive Surgical is located. So we were just discussing earlier, but there's some new faces. So has anyone heard of Intuitive? No one's ever heard of it? You've heard of it? How have you heard of it?
Didn't they make the Da Vinci?
The Da Vinci, yeah. So maybe you've heard of the Da Vinci surgical robot, not the name of the company. Has anyone heard of the Da Vinci robot? Okay. So how did you end up hearing about it? Through a family member, or?
No, just doing research.
Yeah. Okay. So Intuitive Surgical makes, and I'll go into this in a little more detail, but makes a surgical robotic platform to do minimally invasive surgery as opposed to open or laparoscopic surgery. I'll go into that in a little more detail. And I'm the Director of Imaging Systems there, so I'm in charge of the endoscopy work. So the robot that we have on the market today is called the Da Vinci. And the company all started from a DARPA-funded grant to SRI. Does anyone know what SRI is? So Stanford Research Institute. So it's a research center in Palo Alto. DARPA funded a program there to do remote battlefield surgery. So the idea is someone in the military had the idea that, hey, we need to be able to operate on a critical patient that's in the field. We don't want to bring a brain surgeon out there and potentially lose that person. So let's figure out how to do this remotely. A couple of entrepreneurs in the Bay Area out of Stanford realized that really the opportunity for this is for regular surgery to replace laparoscopic surgery. So they licensed some patents out of SRI, also licensed patents out of IBM and MIT, and in '95 brought these technologies together and formed the company in Mountain View, which is in Silicon Valley. So in '95 the company was founded. In '97 we did the first human cases with a system that was called Lenny, after Leonardo da Vinci. And then in '99 the first Da Vinci system was launched full scale. And the idea was that it was going to go after cardiac surgery. So in the medical device market, pretty much everyone tries to go after cardiac surgery first, because if you don't know anything about it, they're highly reimbursed. Cardiac surgeons usually have a lot of say and control in the hospital, and there's potentially a huge patient value. Your patient's either going to live or die from this surgery often. So they went after cardiac surgery initially, but what they had heard of those things, but what they hadn't appreciated is how risk averse cardiac surgeons are to taking on new technology. As one cardiac surgeon explained to me, if he loses one patient in the OR, then he will stop getting referrals from all his cardiologists, and his business will just shut down over a single patient. So they're extremely risk averse. They don't like to take on new technology very easily. And so the company struggled for several years trying to push something in the cardiac space. And there were several systems out there being lightly used. And this is, the company was kind of bouncing along. It wasn't clear if the company was going to make it or not. And then a urologist got a hold of the system. He's from Henry Ford Hospital in Detroit. Got a hold of the system and started doing prostate procedures with it. And it turns out that there's also a very high patient value for prostate surgery. So before robotic surgery came along, your options for prostate surgery were pretty limited. You were going to have open surgery, so they would cut you open from your belly button to your pubic bone. And it's a very bloody field, very hard to see. And they're going to cut out the prostate, and there's a lot of nerves that surround the prostate. And so you'll likely come out of the prostate procedure never having sex again and not having bladder control, or your outcomes. But you've got the cancer out, so you're not going to die of cancer at least. So pretty good cancer control. Your chances of surviving cancer were very good, but your lifestyle outcomes were pretty awful. And the reason for that is because there's all these nerves that surround the prostate, and it's very difficult to see those nerves and to cut out the prostate walls until preserving the nerves. He got a hold of the system and he thought, that's exactly what I need to be able to do this procedure the right way. What the system enables is the ability to do intricate tissue dissection and cutting with magnified image and stereo perception, and it enables better outcomes for the patient. And he did a series of 100 patients and published that data and actually showed that outcomes were better than open or laparoscopic surgery. And at that point, the company sort of took off at that point, and it was adopted as a system to do prostate surgery by urologists. And then in 2003, some additions to the platform. We added an additional arm. In 2006, we came out with the S, which was a kind of an update to the original Da Vinci system, where the robot arms were in hand. And then in 2007, 3D HD was launched, so all the imaging was done in stereo. And then today's current system is called the SI, Da Vinci SI, and so it is made up of the patient card, a surgeon console, and a second surgeon console if they want that. This is for training or driver's ed purposes, and a vision card that houses the video system. So I'll go into a little more detail about how we got here. So as I said, this is the kind of scar you'd have if you had a hysterectomy, if one were to have a hysterectomy. Very, very large incision and pretty nasty scar after this. But it allows the surgeon to get a large field of view, exposure of the uterus, and to be able to see what they need to see and be able to get their hands in there. This was replaced to some extent with laparoscopic instruments. So these are instruments that have a long shaft, have some type of a end effector at the end of the shaft, and a trigger and a handle at the back end so they can manipulate the end effector. But as you can imagine, it's very difficult to do surgery with this. Now you minimize the incision, so now you just have 3 small holes that these go into, and a camera. But it's made the job a lot harder for the surgeon. So it works for simple procedures where there is it's relatively straightforward, not a lot of nerve tissue to worry about, but it's very challenging for the surgeon. And they've lost their 3D vision, they've lost their dexterity of their hand movement, and they've lost their orientation because the camera is not necessarily positioned to the view that they're accustomed to. So the camera might be upside down relative to where they're standing and where their hands are positioned. So that's what the robot does, is it essentially emulates open surgery. So it has a full range of motion for the wrist, for we call wristed instruments. So all the instruments have 6 degrees of freedom at the tip. 3D vision, so it's actually like a binocular microscope. It's actually 2-channel optical microscope. Natural hand eye alignment, so up is up, right is right, left is left, and intuitive motion. And this is just a little video showing the tip of the instrument. This is looking at the video. So this is showing some foam simulated tissue. And you can see these are the controls. So the surgeon is sitting at the controller, and his hand motions map directly, the robot maps his or her hand motions directly to the motions that are required at the robot side. So the surgeon's looking inside of this console, which is displaying the stereo video image. His hands are manipulating the controllers here, and then the slave robot is simply mimicking his hand, a scaled version of his or her hand motions.
Is there tactile feedback?
Gross tactile feedback, in other words, big forces, but not small. It's not small forces. So you couldn't feel the pulsating vessel, for example. But if you bump up against some tissue hard, you'll feel that. Surgeons, say that they don't actually miss the tactile feedback, that the visual cues are so good. So they're seeing the image like they've never seen it before. They're seeing it up close with no blood and with about a 10x magnification and in stereo. Before, they either had an open surgery with lots of blood and they're 18 inches away, or they are looking at a 2D screen that's somewhere in the OR, and again far away. So when they're sticking their head in this console, they turn the lights down in the OR, so they have very high contrast, and the image is completely filling their field of view. So it's a very immersive experience. Surgeons will tell you that it feels like they're inside the body, right there in the surgery. So this is the tip of our camera. It's actually it's 12 millimeter diameter shaft, but it's actually two optical lens trains to create the stereo image. So where is this going? So in the near term, we're pushing next generation instrument technologies, different types, delivering energy of different sorts, laser, electrocautery energy, ultrasound energy, and enhancing the vision system. So taking advantage of CMOS technology, 1080p, and increasing the resolution, increasing the color and fidelity of the system. Beyond that, we're developing new robotic architectures. We're incorporating networking and telementoring, so remote mentoring, and additional enhancements to the vision system beyond just kind of the basic things. Longer term, there's image guidance using, say, preoperative CT data to blend it using registration techniques to register it with live video. Simulation systems so that for training, haptic feedback to your question, and tissue characterization, things like spectroscopy or in vivo microscopy to do histology. And then beyond that, people are talking about full automation. I don't know if we'll ever get to that. And doing telesurgery, like the original vision for this was to do remote surgery and enhanced training. So one of the things that's really interesting that now that you have, once robotic technology becomes accepted in the OR, now you've broken the paradigm of surgery a little bit. So before, the surgeon had to be scrubbed in, they had to stand over the patient and do the procedure open or potentially laparoscopically, but they are in a not very ergonomic position, very uncomfortable. Lots of surgeons will tell you that they have a lot of back pain, a lot of neck issues, and their careers are effectively shortened because of that. So we've kind of broken that paradigm in that the surgeon now can sit down. They don't have to be scrubbed in. They can sit down. They can be relaxed at the console, and in a sense, it gives them more time. So an example of that, I was speaking with a cancer surgeon in Arizona recently, and he said that he was in a procedure where he accidentally nicked an artery, and started bleeding, and it was in a very dangerous situation. But with the robot, he was able to clamp the artery with one hand, and then when you pull your head out of the system, it automatically locks up all the arms, so that if you're not in the system, it's frozen. And so he clamped the artery, pulled his head out, stepped away. You can let go, and the robot holds on. It holds position wherever you were last. And so the robot is holding onto that artery for him while he's able to step back, think about his situation, talk to his team, establish a plan for how they're going to seal this artery and then the artery. And then he was able to take 5 minutes over that and then go back and do what he needed to do. He said if that had been either an open or a laparoscopic procedure, if it had been laparoscopic, they would have struggled to try to stop the bleeding. The blood would have been coming out. They wouldn't have been able to see. They would have had to cut open, go open, and try to get in and find the bleeder in this immense amount of blood. And there's a good chance they might have lost the patient. So it gives them a new paradigm of dealing with surgery that they've never had before. In addition, it also, now we can feed them information, additional information that either they might have had access to but didn't have a good way of viewing it or a good way of taking it in, because they're having sensory overload already. They're standing above the patient, they're trying to manipulate 4 or 5 instruments, and then looking at a screen. Now they can be seated here and we can actually provide them with additional information from other sources that can feed their decision making during this procedure. Here's a quick look at some robotic architecture. So this is a single port architecture. The idea being that we can do the procedure through a single hole in your belly button. So all the instruments would come through a single hole, the camera's on top, and these are the instrument arms here. And this enables access to different kinds of surgical procedures than compared to, say, a multi-arm instrument. Feel free to ask any questions, too, while I'm going through this. Another robotic architecture is mounting the instrumentation to the table itself or hanging it from the ceiling. And as I discussed, the console. So the console, if we have 2 of these, we can do a driver's ed where they can work collaboratively or do training, one surgeon can train the other surgeon, and shorten learning curves, or the second surgeon can actually assist. And then telestration or telementoring, as I mentioned earlier. So there's been some experiments done where they've done the surgery remotely. But actually the more interesting thing and what the market is at, what hospitals are asking for is the ability to train remotely. So rather than having the expert surgeon in Paris do the procedure in Colorado, they would rather have that expert surgeon train the surgeons in Colorado so those surgeons can then train other surgeons locally and kind of expand that. And we're building out a network of systems worldwide. We have about 1,500 systems installed worldwide. And then this is simulation. So we built up simulation systems that simulate the robot and allow surgeons to practice without requiring a full robot to be there. And so they can log hours and practice different surgical technique through this computer-driven simulation system. So this is an imaging application. So this is what we call tool tracking. Let's see. So we can track the position of the tool with, you notice underneath there's some fiducials on the tool. So with the live video image, we can do real-time position tracking of the tool combined with the feedback position of the arms from the encoders. We can know exactly where the position of the instruments are. So the applications for this are to measure a mitral valve, for example. So when they're placing a repair mitral valve, this isn't real, by the way, so it's plastic. I see some people are making faces. What they'll do in the procedure is they need to size the mitral valve precisely, and they have a few different, they come into the procedure with a few different mitral valves, pre-sized mitral valves. This allows them to measure the circumference and figure out exactly the size that they need. It's also used for measuring tissue structures like colon or things like that. So, a little bit of the history of laparoscopic imaging. So, the first endoscope was developed in 1805, and the technology actually hasn't changed that much. You have an objective at the front end, then you have a series of glass rods like these that simply relay that image over and over again, all the way to the back end, where it's then imaged on your eye or into a camera, into a CCD. That's what we do. We basically attach this to a CCD camera and feed that image live into our display console. Now that, as you can see, essentially that's what they're doing today, and the technology for this really hasn't changed that much. The optics hasn't changed that much. So ours, as I mentioned, stereo. So we actually have two channels, two camera heads on the back end. Those two camera heads both go into two displays inside of the surgeon console. So a left-hand display, right-hand display. So we create very high-quality stereo perception. So with a lot of stereo, anyone have a 3D television? Or did you go to see Avatar or something like that? So that was done with passive glasses, polarized glasses. And the problem with those is you'll get lagging effects, or there will be anomalies because both eyes are seeing the same screen. A lot of different types of artifacts can be seen if you know what you're looking for. But in this system, you have each eye is independently seeing a full 2D image, and it's not shared with the other camera. So as I was saying, there's an opportunity now where we can add new imaging capabilities. So diafluorescence, spectroscopy, ultrasound, MRI, CT data, high-resolution microscopy, non-fluorescent. So really the idea of this talk is more about a little bit about the applications, kind of what we're doing, and the fact that this now opens up the opportunity for maybe imaging modalities that exist but aren't very widely used because maybe the user interface wasn't there. And so in a sense, it's a new type of user interface for displaying or providing information. And also, there's a lot of interesting imaging problems here for imaging related like spectroscopy. So being able to do real-time live tissue characterization. The surgeon wants to know where's the cancer tissue and where's the healthy tissue and where's the boundary. And if I can show them that boundary real time, then it'll allow the surgeon to make real-time decisions about where they're going to cut and remove tissue. And so that's the goal of all of this is to provide the surgeon with more real-time information to allow them to make surgical decisions. So what types of pre-op data? So you have CT data, MRI data, etc. And this is all taken pre-operatively, but there are lots of folks, I don't know if anyone here is working on image registration. They might be doing image registration type stuff. So you take some type of pre-operative images and you want to align those in real time to a video image. So you have to recover the surface structure of the video image and then map that, and it's probably changed, so you have to figure out how do you deform the live video image to match up with the CT image that was taken with a different deformation, and then have that update and deform in real time. And then you can provide, if you have an image of where the cancer is inside the kidney, Now you could show the surgeon in real time where inside the kidney is located, the shape and the structure of it. And as opposed to what they do today, they purely have a video image of the surface and they have to essentially they're in effect making that mental model themselves of where the tumor is from looking at the pre-op CT data. Well, here's another imaging challenge. So you can do the imaging piece, but now how do you display the information to the surgeon? So as I mentioned earlier, you reach a point of kind of information overload. I think it must be, whoever designed this probably never actually intended to fly it themselves. It's a big problem. One interesting study we've done, we had the ability now with the tool tracking, we had the ability to actually display to the surgeon which hand was holding a cautery tool, meaning a tool that could produce electric current, burn tissue, cauterized tissue. Because sometimes they would get mixed up and they'd think the cautery tool was in their left hand when it was really in their right hand, and they'd end up burning the wrong tissue sometimes. So we thought, well, wouldn't it be nice if we could like highlight that tool that was cautery. So we did some experiments putting icons on the display, and we found that unless you put the icon right in the center of the image, the center, say, center region, just say like right in here, or right in here, you didn't put the information right in the center where they were focusing all their attention, they didn't even see it. They just completely passed it by. And it's because they're so focused on the task at hand that they've completely tuned out everything else. Now they go in and out of that focus. So when they're doing something very intricate and careful, they go into focus and they completely tune out any other information. And then when they finish that task and they're now maybe more into a navigation mode where they're looking around, that's when they can take in more information, but they may always go back to this. So it's something to be aware of as you're thinking about these imaging problems. You also have to think about, well, how am I going to eventually get this information to the user in a way that doesn't have their head explode. So one of the ways that we're dealing with it is basically picture-in-picture right now, but so there'll be the live surgical image, and then we can pipe in external video through some external input sources and have picture-in-picture essentially. So they have ultrasound. This is an ultrasound tool, so they can have ultrasound in one corner and the patient vital signs monitor coming in the other side. This is another tool that we're playing with to display some additional information. Is that better?
Yeah.
So we can bring in some preoperative CT data and then use now instead of using the controls to manipulate the instruments, we can use the controls to manipulate a mouse, essentially, a mouse pointer. So we can manipulate this three-dimensional data set with the surgical controls, just deactivate, the instruments. So they can use this real time to load in a pre-op CT data set, look at it, look for information, and then go back to the surgery that they were doing. Did I work on anything like this? No CT people in here. Well, you're doing some CTs. Yeah. Right. So this is ultrasound, an ultrasound instrument. So this is a linear array ultrasound transducer attached to one of our instruments and allows us to manipulate and articulate the tip. So we can put this into the robot. The robot can control this, and the surgeon can control the articulation of the tip. This is a kind of a video of this. So you can see there's the ultrasound image, and you'll see in a second. So there's the instrument. So the surgeon is controlling it and holding it underneath this tissue, and you're getting this live ultrasound image. And the nice thing about this is, what's their alternative? The alternative is to have a patient side person hold the instrument and do this manipulation. But as you can imagine, it's not a very coordinated dance. So the surgeon says, wait, stop there, no, go back a millimeter, no, back the other way a millimeter, a little bit to the right, a little bit to the left. And it's challenging, they can work through it, but it's obviously better if they can control the instrument directly themselves. So by integrating it into the robot. Then this is just a way we've come up with of displaying the information. So spectroscopy, anybody working on any kind of spectroscopy in here? No? Okay, that's not for sure, somebody would be doing that. So, everyone knows what spectroscopy is, right? So the idea is that with a spectrum, either in the visible or near infrared regime, you can extract tissue parameters from that. And then the holy grail from that is, can you see cancer, or can you see nerve tissue, and differentiate one tissue from another type of tissue, and then color that tissue in the video image a different color, like bright green, so that it's very apparent to the surgeon what tissue is what, and then again they can make real-time surgical decisions based on what they're seeing. I think a lot of folks are working on this, and folks at MIT are working on doing spectroscopy for cancer imaging. It's an interesting field, and again, it'd be highly valuable area for surgery. Then there's fluorescence imaging. So this is where either you're taking advantage of natural fluorescence that's in tissue, or you're injecting some kind of a dye or a marker that preferentially goes to the tissue you're interested in, and then when that marker is excited with the right wavelength of light, it fluoresces, and then you can image that fluorescence. Again, same idea is to be able to differentiate different tissue types based on this absorption of a dye in the tissue of interest. And then autofluorescence is essentially the same idea, but the tissue has naturally occurring fluorescence. So by exciting it with the right wavelengths, it fluoresces at different wavelengths, and you can see different types of structures of interest. Narrowband imaging is an imaging technique where you can highlight just the superficial surface structures by focusing on the shorter wavelengths of light.
Can you just comment a little bit on what your optical platform is that you're getting all this, all these images?
So each one is a different platform. Okay. The requirements for a spectroscopy system are different than the requirements of a fluorescence system, different than autofluorescence. So it kind of depends on which one, but let's just say fluorescence, for example. So it's a relatively straightforward optical system. You have glass optics that pass light through the region of interest that you're in, let's say 400 to 800, 900 nanometers. And then depending on your marker, the marker usually has to be excited with some, like a laser. And so there's a laser that excites the fluorophore at whatever wavelength. Let's say it's like, for example, there's a dye we use called ICG. So ICG wants to be excited at 800 nanometers. So we have an 800 nanometer laser, excites the ICG fluoresces at 830. So we have a filter in the camera that blocks the 800, and it's sensitive to the 830. And so we pick up the fluorescence from the ICG in that way.
Is it through?
Is it through an endoscope?
Okay. So you've got the pump going out on a fiber and pressing the.
So we have optics that capture the image, and we have light fibers that deliver the illumination. So we have light fibers that deliver white light illumination, just for the white light image, and then through those same fibers we carry the 800 nanometer laser light. And then light hits the tissue fluoresces, we pick up the image on the camera, and then by turning the laser on or off and turning the white light on or off, you can switch modes, either fluorescence mode or a normal white light mode. And then we can process it on the back end and blend it, do all kinds of things to kind of interleave the white light image with the fluorescence image. And then in vivo microscopy, so I think there's several folks in here that are working on microscopy. microscopy. So this is a very interesting field. Again, it's related to how do you give the surgeon more information. In this case, it would be trying to give them information about the pathology of the tissue. Is this tissue cancerous or not? And there are companies that, several folks that have developed small fiber-based microscopes. So you can deliver a fiber to the tissue and capture a microscopic image of the tissue surface and get an image like this, kind of a cellular level image to look at cell structure and look for pathology. So it's something that we're investigating. The challenge with this is the field of view is very small. So the field of view that the surgeon wants to work with is on the many millimeter scale, centimeters, multiple centimeter scale, and they're making cutting decisions on the many millimeter scale. But these images, this might be 500 microns across. So there's a challenge there. How do you collect enough information fast enough to give the surgeon something relevant to work with? Yeah, I can see, great, I can see that that's cancer, but if you just told me over the size of a pin, and I need to cut out this entire prostate, which is the size of a walnut, and so it's just impractical. They need to be able to collect that data fast enough to make it provide real-time information. So this is some fluorescence images. I'm just going to skip that, go straight to this. So this is ICG. I mentioned ICG earlier. So you have a live white light image, and then you have ICG that's injected, and the ICG is fluorescing at 830, and we're exciting with 800. So this image is just the red channel of the camera, and the red channel is only seeing the fluorescence light. So it's only seeing, and we've turned off the red. We play some games to kind of recover the red to create a white light image. But essentially, if you just turn off the red channel, you get a grayscale image in the red channel. And that's the ICG fluorescing. And then this image is if we take this grayscale image and alpha blended green back into the color image, we can false color this thing, this crazy green color that you would never see inside the body. Anyway, so it's very easy for the surgeon to spot this. And that, in this case, this is biliary tree. So for a gallbladder removal, which is a very common procedure, one of the complications is that they will accidentally nick some of these vessels, and it'll end up resulting in, after surgery, you'll have complications and very bad outcomes potentially. So to allow them to see these structures very clearly, you can see, here's what it looks like if you don't light that up. So you can see it might be easy for them to make a mistake, and things just get buried or hidden in the rest of the tissue. So this is a cardiac application. The ICG is flowing preferentially through the large vessels, and so you can see it's been injected, it glows and it lights up. And so it allows the surgeons to identify vasculature or to look for leaks if they've done, say, a cardiac bypass. This is a bypass procedure. So they've taken a vessel and grafted it to another vessel, and they're hoping to have blood flow through here. But you can see it's dark, there's no blood flow, and so in this case, after injecting the ICG, you'll see blood flow through that vessel. And then this is a dual bypass, so there's actually, you'll see these two vessels will light up here in a second with the ICG. And again, what you're seeing is it's not colored on this one, this is just the grayscale, but everything that's bright is the fluorescing dye. So another interesting property of ICG is that it's taken up preferentially in healthy kidney tissue, but diseased tissue stays dark. So this is actually a kidney that's been excised, and the Everything that's glowing super bright is ICG, and the dark part is cancer. And so you can see why it would be easier for the surgeon to realize where to cut. So this is imaging the lymphatic system, so lymph nodes. So after a cancer procedure, the surgeon will often want to remove several lymph nodes so that they can do biopsy on those, the pathology report, and determine if the cancer's gone into the lymphatic system. So in this case, the ICG tends to preferentially be absorbed into your lymph nodes. And so you can use you can see there's the picture without lighting it up. You can't really, you can see that it's a little darker right there, but not much. Now once you've found that location, you can remove it. So in this case, the surgeon has traced, they're flipping between modes. So there's the fluorescence mode where they can see this trace of the lymphatic channel. They're going to follow this lymphatic channel to the lymph node, which glows really brightly because it's absorbed a lot of ICG, but it's underneath the tissue. So you'll see we'll flip modes back to white light in a second here. And in white light mode, you can't really tell. I mean, it's a little darker in there, but you can't really tell. Now they're using the cautery tool to buzz and burn the tissue in little spots all around, so they're essentially marking this location, so that when they flip back into white light mode, they'll know where they are. So there's white light mode. See the burn marks? Okay, and the lymph node is right there. But you wouldn't know it unless you had seen it. Now we've sped up the video here. Yeah, either the surgeon or the system is that fast. The system's that fast, the surgeon's. And now they're just flipping back and forth so to cut out the lymph node. And so the idea is they will now be able to take that sample to the pathologist, get the report, and instead of spending 2 hours hunting for that, or alternatively, what would they have done? They would have taken out a very large section of tissue, knowing that somewhere in here I'm going to have a lymph node, just from the anatomy. They know that where the lymph nodes are generally. And they would take out a large section of tissue. So this will help them, this will avoid that, the need to do that.
So how do you get that out once you've grabbed on?
So you would pull it out through, like a small sample like that would be pulled out through potentially the same port that instrument went in, or they will bring in a plastic bag, and drop it in the bag, through another cannula port. So they drop it in a plastic bag and pull it out through a plastic bag, through a small incision, about 1 centimeter in size. And that's how, if you're having a laparoscopic partial nephrectomy, so that's the partial removal of the kidney. If you had kidney cancer, they would do something similar. They would cut out the portion of the kidney, put it in a bag, and pull it through a small incision, so that hopefully, you would only have a few small holes compared to a normal kidney procedure, which is they will cut you from kind of the top of your hip bone up to your rib, and it's a very, very painful incision to recover from. So, coming from an imaging background myself, Intuitive is really a robotics company. That's how they started out. But I think the future of robotic surgery is really going to be driven by from the imaging side of things. On the robotics side, things can improve in small steps. So the articulation mechanisms can get better, the motors are going to get better, encoder technology is going to get better. So the robotics is going to improve, even to the day where you can imagine there will be snake-like robotic systems. But, those are going to be incremental improvements in the technology. I think the next real disruptive technology improvements, the big leaps, are going to come from the imaging side of things, from advancements in camera technology, in computational technology, and computing horsepower. A lot of these algorithms actually are out there, exist for doing solving complex matrices, very large complex matrices for inverting CT systems, for example. However, you can't do that in real time. The computational hardware is not there yet to do it, but I think over time that's going to catch up, and so a lot of opportunity exists for imaging people in the worlds of spectroscopy, fluorescence, CT, ultrasound, to provide three-dimensional real-time data that's now is very hard to get. But with a platform like this, we now have created the delivery device, the user interface for it, and now we need folks like you guys to kind of invent the algorithms and the hardware that can do it in real time and integrate it in a way that would say video would make sense to the surgeon. So I saw this. Yeah, that's what they're doing today. Making Superman do that. So, any questions? We have time for a few questions.
How many hours of training would a surgeon go through before he would begin using the equipment in the operating room?
So the training is, we offer different kinds of courses, introductory courses, and advanced courses for surgeons. So typical courses are like 3 days, where they'll come in and they'll train and learn the system, and learn the procedure steps. And then the hospitals will dictate then what training they need beyond that. So their particular hospital has certification requirements, so maybe they have to do 20 hours of proctored surgery before they can drive on their own. But it differs by hospital. I think, people ask, well, what's the learning curve for robotic surgery? And, I think that number varies between something like 20 to 50 hours of console time before you start feeling really proficient.
You mentioned that some surgeons have been uncomfortable to try this new technology that's not totally tested. I wonder how patients feel about it. Have you had any feedback on that?
Yeah. So I think it's mostly true for new medical products that clinical outcomes is what matters. At the end of the day, did it make a difference for the patient? And so we've seen with the robot that the surgeons who have adopted it, they've published papers and series of papers, and those papers have shown great clinical outcomes. That tends to drive, because of the internet and because that information is available, we've now seen it, lots of patients who are coming to the hospital very educated. They come in and they say, I read this paper from so-and-so, or I saw, these links on the internet to better outcomes and why, with robotic surgery, and they're coming in demanding and asking for robot, or at least asking about it. So absolutely, I think, it's first, I think, driven by patients and surgeons together, because the surgeons, of course, learn about it, and that then drives hospitals to make the purchase. And we've seen hospitals buying systems simply to increase their revenue growth, because it does draw patients. Patients will travel now as they get more educated, and if they're not afraid to travel, they'll travel, to instead of their local hospital, they'll travel the 2 hours or the 5 hours to the bigger hospital that might have a system like this, so they can get that procedure done. So I think absolutely, it's being driven by patient awareness.
You touched on this, I guess, briefly at the end, but I was hoping you could comment a little more on the image processing that it takes. A lot of the videos you showed us, I imagine that there'd be a good amount that would go into on the algorithmic. And
yeah, some of the fluorescence, so the fluorescence stuff that you saw there is kind of on the lesser side. Those systems work simply by capturing the fluorescence light into one of the channels of the CCD and doing some minor manipulations to it to overlay it and alpha blend it in real time. So it would be only line buffers, not frame buffer type delays. Now some of the other things, like the preoperative CT work, that still is a research project, because even though some of the algorithms exist out there to do the soft tissue tracking,
they're not fast enough.
they're not fast enough. They're not fast enough. And the spectroscopy work is, they're still trying to figure out, they're still at the stage trying to figure out, what is the right spectral signature that gives me, cancer detection. Again, those algorithms will be slower as they exist today, because they're looking at an entire spectrum. But once they isolate a few wavelengths that are actually critical and actually, useful for the classification, then those algorithms should be relatively fast. I would expect that they'd be able to do this close to real time.
Does your company do that sort of stuff in-house?
Some of it we do, some of it, some of it we have at different levels. Some of it is very much, kind of on the engineering floor, manufacturing, shifting into manufacturing and kind of in ready to productize. Then we have groups that do applied research that are more kind of looking at 3 to 5 year out type technologies, and those folks are, maybe kind of what you were doing here. You'll have it's sort of a PhD thesis type work. You've got your lab bench and you're just trying to prove basic concepts, but with a focused product and concept in mind. And then we have people that are sort of even further out than that. They're working with universities and on just kind of some basic fundamental technologies and exploring. We have research grant money that we give to universities for exploring new areas. So we do a little bit of everything, just depending on the maturity of the technology. I think there was a question over here.
Back over.
Okay, yeah.
So aside from the surgeons who often make the overall switch to this, are there barriers? So you mentioned prostate surgery and maybe cardiac. Are there barriers to becoming a general surgery tool for any surgery I can imagine? Or
Yeah. So we do lots of different. We cover lots of different specialties. So it's actually a very generic tool. So we are in cardiac for mitral valve repair and bypass surgery. We're in urology for lots of procedures, prostate, cystectomy, bladder procedures, kidney procedures. We're in GYN specialty for hysterectomies, fibroids. And so within each specialty, it kind of is, the adoption is driven by specialty, really. So as you can imagine, what happens is, it started out in urology. So a urologist got a hold of it, and he started doing prostates with it. And then he became very proficient with prostate surgery, and lots of other folks around the country, urologists, started becoming proficient in prostate surgery. Then, you can imagine, so now they're doing prostates on Monday, they have a kidney procedure on Tuesday morning, and then they think, well, you know what, I think I can do kidney with this. And so they work with Intuitive to develop that procedure, and then expand the procedures that they work on within their specialties. So now kidneys, partial nephrectomies are done with it, and that same phenomenon happens in other specialties, GYN, and in general surgery as well. So we'll start in one area where there's a lot of very clear clinical value, but as they become proficient with it, they expand into other procedures that might not have been their first choice, but because the tool is there, they know how to use it, they trust it, they understand what benefits it brings, then it makes sense for them to then apply that to different procedures.
What is the typical cost of a robotic prosthetic system?
So the robot itself is about 1.5 million, and then the instruments, the instruments are 10-use instruments, meaning they're used 10 times in their autoclave, sterilized between each use. So the instruments for a single procedure on average cost about $2,000. So the return on investment for the hospital really comes from the fact that patients have reduced complication rates. So they're staying in the hospital less, they're having fewer transfusions, less blood loss, fewer complications, shorter hospital stay, and then better clinical outcomes, long-term clinical outcomes. So all of those things result in cost savings for the hospital that amortize the cost of the robot. Does that answer your question?
From a simulation standpoint, you showed earlier that the doctor was manipulating a couple tools and moving rings, but can doctors actually perform simulated surgeries? For example, the kidneys or prostate, is that available to the doctors?
It's a good question. I'm not sure. I mean, I don't work on that particular project, but I think that right now it's primarily task-based. In other words, folks are learning, suturing maneuvers. So it's maneuver-based. Learn how to suture, learn how to tie knots, and learning how to, utilize the various features of the instrument, learning how to control the instrument arm and the hand. I think people are working on developing simulations of a full procedure to take them actually through the steps of surgery, but I don't think that has launched yet, but it's coming. Yeah. That's actually one of the biggest challenges is training. Is right now these surgeons they don't know how proficient they are. They get trained, they go through training classes, but it's an early technology, so we're working with other outside folks to develop testing systems and testing mechanisms to be able to provide feedback for their proficiency. Anything else?
Thank our speakers.